A box on a table is attached to a string that goes over a pulley and is attached to another box that hangs over the edge of the table. Find the tension in the string and the acceleration of the box. Now, we said that the string here is what attaches the two boxes to each other, which means whatever the acceleration is of this box must be the acceleration of this box, right? And whatever the tension is in this piece of the string must be the tension in that piece of the string because it's the same string, right? Okay. So with that being said, let's do an F-net statement of the box on the table, all right? Yes, we are. Very good. So we're going to do this one first. All right. Tell me the forces acting on that, please. Sean. Okay, good deal. Excellent. Now, did we say that there's any friction in here?
Yeah, there's a color.
Okay, cool. Then yes, you're right. Very good. Okay. So we've got a frictional force. Now, what kind of friction do you think this is going to be? Kinetic, because that box is going to be sliding along. Very nice. Okay. Now let's go ahead and determine which of our F-net statements are we going to do. Are we going to do F-net statement in the y-axis or in the x-axis here? Why? Because that's the only axis that it's moving in. Okay. All right. So we've got our F-net in the x-axis is equal to what? Very good. Mass times the acceleration in the x-axis. Do we know the acceleration in the x-axis? No, but do we know the mass? 2 kilograms, right? So we're going to say 2 kilograms times whatever that acceleration is. Okay, what's the second F-net statement in the x-axis? So very good. Minus the force of friction. Okay. Do you know what the force of tension is? No. Do we know what the force of friction is? Does friction have its own formula? Yes. What is the formula for friction? No. Mu times the normal force. Very good. So it's going to be mu times the normal force. Does normal force, how are we going to get that? How are we going to get the normal force out of this? That's going to be the y-axis, right? Okay. Now, let's take a look here at this box and just kind of do a little shortcut because we don't want to have to write the F-net in the y-axis if we don't have to. Is this box accelerating in the y-axis? No. So what must be true about the force of gravity and the normal force? Equal and opposite, right? So if we could figure out what the force of gravity is, then we can figure out what the normal force is. Does the force of gravity has its own equation, which is? Very good. Mass times little g. Okay, so go ahead, type that in your calculators if you must, and tell me what the force of gravity is and therefore the normal force. Josh? No. Garrett? Very good. 19.62 what? What's the unit here? Newtons. Very good. Okay. All right. So now we can come down here and we can say 0.3, that's our coefficient of friction, times 19.62 newtons. And we can figure out what our frictional force is. So please do that now. Isaac. 5.886 newtons. Good. So up here in this F-net statement in the x-axis, the summation one, we can go ahead and put that in there. We can say tension force minus 5.886 newtons. Everybody okay with that? Now what do I do? Set them equal. Very good. So I'm going to say the force of tension minus 5.886 is equal to 2 kilograms times acceleration in the x-axis. What do you notice about that equation? There are two unknowns. And if you have two unknowns, what do you need to have to solve it? Two equations. Very good. If you've got two unknowns, you have to have at least two equations to solve them, okay? So that means we've done everything that we can do with this first box here. So now we need to come over and get some equations going on that second box, all right? So let's do that. What was the mass on that one? 1.5. Okay. So what do you want to write down for the second box? Freebody diagram, okay? So Freebody diagram, what axis are we concerned with? Y-axis, okay? So tell me the forces acting on the second box. Adam? Okay, very good. The force of tension is up. And force of gravity going down. Very good. All right. Any other forces acting on that second box? No? Okay, cool. So now we're going to write our F-net statements, right? Okay, so we've got F-net, and what axis are we in again? Y-axis, very good. What's the first one going to say? What acceleration? Okay. Now, what do you think about this acceleration in the y-axis? Which way is that box going to move? Down. So this needs to be a negative acceleration. Okay, so make sure you put your negative sign there. If you don't, that's going to mess this problem up, and you will not get the right answer. Okay. All right. Now we do know the mass. What's the mass? Okay, 1.5 kilograms times acceleration in the y-axis. I'm going to factor the negative sign out front because I can do that. So that's the first equation. Now what's my second F-net statement in the y-axis going to say? Okay, so what's that going to be? Very good. The force of tension minus the force of gravity. All right. Do we know the force of tension? No. Can we get the force of gravity? Doesn't that have its own formula? What is it? Very good. Mass times little g. So that's going to be our 1.5 kilograms times 9.81 meters per second squared. What's that give us? That's a naked number. Very good. Okay, so now that I have both of my F-net statements, what do I do? Set them equal. So I can say negative 1.5 kilograms times acceleration in the y-axis is equal to force of tension minus 14.715 newtons. What do you notice about that equation? Two unknowns left, okay? But we have two equations now, and they're related to each other because the force of tensions that we see in both of our equations are the same force of tension, and the accelerations are actually the same also. Even though in the other one we have it as a sub x, and this one we have it as a sub y, we're going to actually remove the subscript now because those accelerations are the exact same as each other. So now we're just going to write them as a for acceleration, okay? So let's group our formulas together. Somebody tell me our equation from the first one, please.
2a equals ft
minus 5.886. Right. You meant to say newtons, I'm sure. Okay. Now, there are a couple of ways that we can solve this system of equations. Hopefully you remember from algebra class. Somebody tell me one way we could do it. Josh? Substitution. That's my preferred method, actually. What's the next one? Elimination. And we could do graphing. We could do matrices. Okay. So now which variable do you want to solve for?
acceleration.
Okay. So let's divide both of these by 2 then. Oh man, that's going to be really difficult. Yeah, I really don't like that. That one's horrible, Shabam. Bad idea. Yeah, I think that would be great. So let's just add the 5.886 to the other side.
That's how you'll be remembered for the rest of your life. I'm going to show other classes.
Yeah. Okay, so we've got the tension force is equal to 2A plus 5.886 newtons. Okay, so that means that anywhere in this other equation that we see tension force, we can substitute this stuff in its place. All right, so bless you. Let's go ahead and do that. So we're going to say negative 1.5 kilograms times acceleration is equal to, now we're substituting this in, 2 times acceleration plus 5.886 newtons minus 14.715 newtons. Okay, so now our equation is in terms of only acceleration, okay? So we want to group the acceleration variables on the same side of the equation, all right? Okay, so what do you want to do? What do you want to move where?
Combine like terms so the newtons.
All right, so we can take this here and combine it with that there. So somebody do that, please, and then let me know what that comes out to be. Yeah. Okay, so is that's what everybody came up with so far? Yes? Okay, so now, again, we've got to get those variables on the same side. What do you want to do? All right, so we can subtract 2A from both sides. Yeah, we could do that. Okay, so
You got to add 1.5 to the other side.
all right. So we've got 8.829 plus negative 1.5 kilograms times acceleration equals 2 times the acceleration. So what now? Now we'll add this, okay? So we're going to say plus 1.5 times the acceleration so 8.829 newtons equals, all right, so now right here you have 2 plus 1.5. What's that give us? 3.5. So that's going to be 3.5 times the acceleration. So now how do I solve for the acceleration? Divide by 3.5. Good. So let's do that. Divide both sides by 3.5. What do we get? Raise your hand. Is this the final answer? It is one of the two final answers. However, are we going to need to use this answer in order to find the other answer? Yeah, so I need every single digit, and then we'll sig fig it. Graham? Perfect. Okay, so the acceleration with the correct sig figs. How many sig figs should we use here? 1. Where does that come from? The coefficient of friction. Very good. So what do I end up with? Uh-oh. Some people forgot the arcane rounding rule. But we stop at that 6. Oh, I always forget what I tell you. Okay, so, all right.
Someone forgot the arcane rounding rule.
Whatever. Yeah, whatever. It will just play the game. All right. So the acceleration is 3 meters per second squared. Okay. Now we're going to go back to one of our previous two equations, okay? So let's see. That's going to be, where are they at? That's going to be either this equation right here, okay, or this equation here. Which one do you want to use? The second one? Okay. So tell me what that second equation was, please. 2a what?
Equals FD minus 5.8.
All right, now we're going to substitute in our acceleration into our equation there and solve for the force of tension. I'm going to go ahead and get the force of tension alone first. So I'm going to add the 5.886 to both sides. You don't have to do that. You could do it your own way, whatever. All right, so force of tension is equal to 2 times 2.522571.429 meters per second squared plus 5.886 newtons. Bless you. Type all that into your calculator, please. That's tough. Yes, sig figs this one, please. How many sig figs should we have? Just one. Okay. All right. Who's got it? Isaac? Raise your hand if you agree with Isaac. 10 newtons. All right. Okay, 10 newtons it is. Easy? Yeah? Okay. All right, so the standard practice that we did here was we came up with two equations and then we did a substitution, okay? That's going to start popping up more frequently. That's the same thing that we did when we had the hanging masses hanging from the ceiling in that one problem. You had to do a substitution in order to get that answer to that question, to find all the tension forces. Same thing here. We had to do substitution to figure out both of these variables. Okay? All right. How much time do I'm supposed to be my own timekeeper now? When do we get out of here? 40? Oh, we got so much time. Let's see. Yes, we are doing another one. All right. Okay, so here we go. Connected boxes. Two boxes are connected and pulled by one end on a frictionless surface as seen below. So we want to figure out what this tension force is in between the two boxes, and we want to figure out what this pulling force is on just the 2 kilogram box, okay? And then, of course, we know that the whole thing is moving at 2 meters per second squared. Give me some ideas. What do you think I should do here? Mark? Very good. I can treat this as one entire system, okay? So I'm going to be able to say that I've got a 7 kilogram mass moving at 2 meters per second squared, right? So what's the net force going to be then? Okay, that's going to be 14 newtons. All right, so I've got that. Now let's see if we can get this tension force in between them. What do you want to do now? What's always going to be our first step here? Free body diagram. Okay, so I want my free body diagram for box 1. I'm going to say the 5 kilogram box is box 1, okay? Yeah. All right, so I've got box 1, free body diagram. Tell me all the forces that are acting on it, somebody. I need a different somebody. Mark? Which way? Okay. Next. Adam? Which way? Oh, very good. Isaac? Very good. Did we say anything about friction in this? It's frictionless, so no friction. Okay, now which axis are we going to play in? The x-axis, because that's the one where the motion's happening, okay? So I'm going to say my F net in the x-axis is equal to what? Okay, there we go. Mass times acceleration in the x-axis. Of course, she meant to say that. So I'm going to say 5 kilograms times, what's the acceleration here? Thank you, Brady. 2 meters per second squared equals what? 10 what? 10 newtons. Very good. And then my second F net statement in the x-axis is going to be equal to what? Sum of all the forces. So tell me what that is, please. Force of tension. Nothing else? All right. So what do I do with these? Set them equal. So I can say then that the force of tension is equal to 10 newtons. Okay? So that's going to be, where is that force of tension? Which one is that? Is that on the end over here, or is that in between? That's the in between, okay? All right. Now let's figure out what this force is over here on the 2 kilogram box. So let's do our Freebody diagram on that one, on box 2. Somebody give me all the forces on box 2, or at least one of them. Garrett? Very good. Which way? Up, okay. And then? Yeah, there's a tension force to the left, yeah, okay. And then there's some kind of applied force to the right. Okay. Yeah, so we could, if we assume it's being pulled by a string or something. Whatever. Okay, I'm doing that so I can differentiate which forces. I don't want 2 FTs up there. Okay, which axis do I care about? The x-axis. So let's do our F net statement in the x-axis. What's the first one going to say? What acceleration, Graham, in the x-axis? Good. Okay. Do I know the mass? Do I know the acceleration? Yeah. So what was the mass of it? It was a 2 kilogram box? Okay. And what was the acceleration? Okay. And so what's my overall net force going to be? 4 newtons. Very good. And then I need to do my second F net statement in the x-axis. Somebody raise your hand and tell me what that one's going to be. Adam? Which is? You said them backwards, bud. Vinay? No. Brady?
Applied force minus.
Very good. Applied force, because it's on the positive side, right? And then we're going to subtract the tension force because that's pointing in a negative direction. So applied force minus my tension force. And then what do I do with those two equations? Set them equal. Now we know something about tension, right? What is that? Equals to 10 newtons. Okay, so I'm going to go ahead and put that in there. So I'm going to be able to say then that 4 newtons is equal to force applied minus 10 newtons. How can I solve for the force applied? Add my 10 newtons to both sides. Okay. So the force applied then must be equal to 14 newtons. Okay. Yeah, we did. This was confirming that. Okay. Now remember, let's go back and take a look here. Remember that the net force on an object is always in the direction of the acceleration. Okay. So since we have the acceleration going in that direction, that means that this right here, that must be the net force. Okay, it's the thing causing the whole system to move. Does that make sense to everybody? Okay, cool. Questions, comments, concerns, suggestions, ideas? 10 newtons and 14 newtons.
Wait, shouldn't they both just be 10?
Oh, yeah, I guess so. Yeah, Brady brings up a good point here. Since we only have one sig fig in any of our given, our final answer down here actually should not be 14 newtons. It should be 10 newtons so that it has one sig fig. Nice job, Brady. Okay, so Libby pulls a 3.9 kilogram box to the right with a force of 200 newtons at a 45-degree angle relative to the horizontal along a frictionless surface. What is the acceleration of the box? Okay, so first thing, let's draw ourselves a picture of what's happening here. Got some kind of a box. It's 3.9 kilograms. And Libby is pulling that box to the right with some 200 Newton force at 45-degree angle. All right. And then, of course, this is a frictionless surface, and we're trying to figure out what's the acceleration of the box. Okay? Now, does that 200 Newton force lie on the x or y axis? No. What do you have to do? Decompose it. That means that you're going to have an x component and you're going to have a y component of that force, right? How do I do that? How do I decompose? Very good. So we're going to say then that the x component is equal to the overall force, the 200 newtons, times, what do we use with x? Cosine. Very good. Times the cosine of what angle? 45 degrees. Now, for those of you in pre-cal, remember the unit for 45 degrees is square root of 2 over 2 for both the x and the y, right? So when you take the cosine and the sine, both of these are going to be exactly the same answer, okay? And then we can do here our force in the y-axis. That's going to be 200 newtons times the sine of 45 degrees. So go ahead, type those in your calculator, and let's figure out what that is. Somebody do the cosine, somebody else do the sine. They should be the same. No tens. All right, Graham, what's the fx, please?
They're the same thing.
The exact same. You just said the same.
Expelliarmus. Go, Graham. Say it again. That's plenty. That's good. Okay, so that must be for both of them. Okay. Now that we have those resolved into their component forces, we want to do a new free body diagram. So we've got our box here, and we've got a force of gravity acting on it. We've got a normal force acting on it. There was no friction this time. We have an additional upward force in the y-axis of that 141, so on and so forth, newtons. And then we have a force in the x-axis here of 141, blah, 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 newtons, okay? Now, when they ask me for the acceleration, which axis is that going to happen in? That's the x-axis, right? Now, since there's no friction in this problem, it was a frictionless surface, do I care about the fact that this was happening at an angle? No. If there had been friction, then that means I would also need to know what the normal force is, right? But our normal force would change. It would be less than normal because we have an additional upward force helping it out, right? Reducing how much that box is making contact with the surface that it's sitting on. Does that make sense to everybody? So we would have to do a y-axis FNet statement and figure out our new normal force, and then we would use that to figure out what friction is, and then we could plug into x-axis and figure out whatever the acceleration is. But we don't have any friction, so I don't care what the normal force is. All this stuff here, garbage. All I care about is this fx, which I have already found over here, right? Yeah, so all I have to do is my force times acceleration in the x-axis. So I'm going to say F net equal in the x-axis equals mass times acceleration in the x-axis. What's the mass? 3.9 kilograms times whatever the acceleration is. And then F net in the x-axis is the sum of all the forces. The only force in the x-axis is Fx, which we already found to be 141, blah, blah, blah. Okay, so then what do I do? Set them equal to each other and solve for the acceleration. So I'm going to say the acceleration is equal to 141 point blah, blah, blah divided by 3.9. That would be fine. Yeah, how many sig figs are we playing with here? 1 because of 200, right? Okay, so what do you come up with? 40 meters per second squared. Some of you are getting in that bad habit of